Picture the absolute tallest mountain on Earth. This diagram shows Mount Everest peaking at 29,029 feet above sea level. But look at Hawaii's Mauna Kea. Measured from its base on the seafloor to its peak, it stretches 33,500 feet. The ocean obscures the vast majority of our planet's massive volcanic structures, keeping them submerged and entirely out of view. Because we live on land, we tend to define our world by what sits above the water, missing the active geologic features that are currently shaping the crust beneath us. For centuries, seafloor mapping meant dropping weighted lines into the abyss. It was a physical, slow measurement, providing a single data point every few miles. Today, researchers use bathymetry, specifically a multi-beam echo sounder system, to illuminate the seafloor with sound. This diagram shows the process. A research vessel emits acoustic pulses in wide geometric swaths toward the bottom. By tracking the ship's speed and how long the pulse takes to ping back up, the system calculates depth in real time, generating a three-dimensional topographic grid. Mapping this data reveals a landscape in the dark depths that is far more active than the surface suggests. Sending sound into the deep is our only way to uncover the tectonic forces that are constantly constructing and destroying the planet's crust. Acoustic maps show that underwater volcanoes are concentrated in three specific tectonic environments. This is a subduction zone. As one plate dives beneath another, magma rises through the overriding crust, often leading to volatile eruptions. At spreading centers, the plates pull away from each other. Magma from the mantle wells up to fill the gap, creating linear volcanic ridges. The third zone is a hotspot, where stationary plumes of hot mantle rock punch through the crust from deep within the Earth. These three mechanisms act as pressure valves, continuously recycling the Earth's surface through volcanic activity. Using the Hawaiian hotspot, the magma plume remains stationary, while the tectonic plate above it moves. This drags volcanoes away from the heat source, creating a chain of progressively older islands, from active peaks in Hawaii to 5-million-year-old Kauai. These peaks start as seamounts, submerged volcanoes that have not yet reached the ocean's surface. If the continuous underwater eruptions remain active and build up long enough to breach the ocean's surface, the submerged volcano officially becomes an island. Once land is formed, wind, waves, and rainfall begin eroding the peak. Over millions of years, the island erodes and the seafloor subsides, turning the peak into a guyot, a flat-topped seamount sinking hundreds of meters back into the deep. Every volcanic island we see is caught in this life cycle, moving from its birth at a hotspot toward inevitable erasure beneath the surface. Even after they sink, these guyots and seamounts serve as critical deep-sea oases. These underwater mountains alter currents, forcing nutrient-rich waters toward the surface to support complex biological webs. The hard basalt of these extinct volcanoes provides a stable surface for deep-sea corals and sponges to attach and grow. However, these same structures also present hazards. Slope failures and eruptions can generate massive tsunamis and pyroclastic flows. Large eruptions inject immense volumes of ash into the atmosphere, which can reflect enough sunlight to temporarily cool the global climate. In the vastness of the deep ocean, these structures provide the habitat needed to sustain life, even as their tectonic activity causes global instability. While eruptions are destructive, the weathering of volcanic rocks eventually produces some of the most fertile soils on Earth. The ocean floor is a dynamic landscape that regulates the recycling of the Earth's crust and the distribution of heat from the interior. Mapping these hidden giants with acoustic technology allows us to read the planet's geologic history and more accurately